I want to create a full-on simulation of the interaction of radiation with matter. Such simulations are used in practice to determine how much radiation dose someone receives when getting therapy for cancer, for example. Now we're going to focus on gamma radiation, or photons. Photons can interact with the particles of our body in a variety of ways. There's the photoelectric effect, which won Einstein a Nobel Prize in 1921. Compton scattering, which earned Arthur Compton another Nobel Prize in 1927. And other various interactions, such as pair and triplet production. Now, Compton scattering is probably the most difficult process to simulate, so I'm going to spend a whole video on it. More specifically, I'm going to show off the beauty of Python and how it can be used to solve these complicated mathematical problems without destroying your hand and wrist doing endless algebra. Compton scattering is very simple conceptually. A photon scatters off an electron and loses some energy in the process. Its final energy is related to the initial energy by the angle at which it scatters. So how do we get that angle? Well, the angle is a random variable, which follows the so-called Klein-Nishina equation. We'll use this information to get a distribution of the percent of energy transferred from the photon to the electron during the Compton scattering process. In a way, this represents the energy transferred from the incoming radiation to us during Compton scattering interactions. In the process, we'll explore what cross-section really means, and we'll use SymPy to solve some pretty nasty algebraic equations. So we have our packages today, not super complicated, NumPy and Matplotlib, as you're used to seeing. We're going to do some animation, so I have those imported. I have the nice plotting style used as well. And of course, SymPy is going to play a major role in this video. One of the main things I want to show off in this video is how powerful SymPy can be when dealing with these horrible algebra equations. So you'll see that soon. So as an introduction to scattering, and scattering is complicated, I have this beautiful picture from David Griffith's book on elementary particles. So I think this is the best way to think about scattering, and I'm going to take a little bit of time to describe it because it's important to really understand what cross-section means. So you have an incident particle in red here, and don't worry about this right now, but there's something here that causes it to move, and it goes in an outgoing direction, and it changes angle by an angle of theta. So it leaves more particularly with a solid angle, d omega. So a solid angle is like if I split this, this is supposed to be a sphere, into a bunch of little almost like rectangles or squares on the sphere. That sort of signifies a solid angle. It's like a theta, but then also a phi, like you're rotating around this way. So that's what the solid angle is here. And so what you have is, imagine you have a beam, rather than one incident particle, you have a beam of particles coming in, right? And so they intersect this area, this black area here, which I'm going to call d sigma. So they're coming through this area d sigma, and they all go through and they all scatter off this thing, and they come out through this black solid angle d omega. So there's an angle here. Well, something to note is that d sigma is obviously proportional to d omega. If I make d omega bigger, if I look for more of these particles that are scattering out through the sphere, obviously the beam that's coming in is going to have to be wider. And if I make this really small, right, then this will decrease as well. So d sigma is proportional to d omega. And it's related through something called the differential scattering cross-section. And so d sigma, it's proportional to this factor, so this is a proportionality, and I'm writing it the actual constant, capital D of theta. What that means is that the proportionality of d sigma and d omega depends on the angle theta that this scatters at, right? So it's different if it's scattering up here versus scattering down here, and this has to do with sort of the spherically symmetric potential, because obviously there's a phi angle that rotates around as well. It could depend on phi, but of course, whether I'm coming in sort of like this, or coming at the bottom and going like this, or any of the angles of phi, it doesn't matter because it's just a spherically symmetric thing. And so that's why I write this proportionality like this. And that just means by definition that d of theta is d sigma d omega. So this quantity d sigma d omega is the cross section. And you might be confused. When I see this all the time, or at least before I was preparing this video, it would always bother me, like, what does this actually mean? Well, think about something like density, rho is dm dv. What that essentially tells you is in an arbitrarily small volume dv, how much dm is there per dv. So what d sigma d omega tells you is how much d sigma there is per scattering angle. So if I look at a scattering angle like this, how much d sigma is there per this black area here? So maybe I'm up here and there's a different black area here. And maybe that corresponds to a smaller d sigma, maybe somewhere up here. And if I'm down here, then I have a black area here, and maybe that's a slightly larger d sigma. So it says how much d sigma is there, like this black area here, per d omega, this black area here. It's very analogous to density with mass and volume. Only here you're comparing sort of an area, and this isn't quite an area. It kind of is like an area, but it's a solid angle. So that's essentially what you're referring to. So think about it as the amount of d sigma you get per d omega, the solid angle. So with this quantity d sigma d omega, you can basically quantify how something will scatter off something else. And of course, you can look at that for many different problems. And the problem we're going to look at is Compton scattering. So that's where this incident beam of particles or whatever are photons, and the thing they're scattering off of is an electron. So in that case, you use some complicated quantum field theory calculations, and you get the following result. You compute this, and I'm not going to look into this in this video, but you can derive it. And you have Re squared over 2. Re is just this constant. It's the classical electron radius. And then you have it as a function of theta. So there's theta. Theta shows up on all these places. And alpha is equal to the incoming photon energy, right? Photons have energy as they come in, divided by mc squared, where m is the mass of the electron. So it's the energy of the incident particle coming in divided by the rest mass of the electron. So that's really important. I'm going to use alpha all the time in this video. Alpha is the ratio between the incoming kinetic energy of the photon and the rest mass of the electron. So that's what alpha is. So it shows up here a lot. So with d sigma d omega, essentially, you can look at solid angles. You can integrate over a certain region and say how much of d sigma does that correspond to. And the beautiful thing about this is this allows for a probabilistic theory. Because if these incident particles are coming in uniformly in this area, right? So they're all sort of coming in randomly. You can say how much of them are going to scatter in different areas, right? That's something I'll get into a little further in the video. So using d sigma d omega, the relation between how much this is per this, if I know that these come in uniformly and these are related, these black areas are related to these black areas, I can determine the probability density function of how these things are being emitted, or the scattering probability density function. And this gets into, of course, this is what the Klein-Nishima equation essentially gives us, is a probabilistic, or a way to obtain a probabilistic thing. For our first problem, we want to find the probability that a photon scatters at angle theta, right? And of course, it's going to be infinitesimally small. So what we really want is a probability density function in theta. So you give me an angle theta, scattering here, and I want the probability density function of that. And if I integrate over all theta on the sphere, it should be equal to 1. So then I get the sort of relative probabilities of things scattering at different angles. So for that, we're going to compute d sigma d theta. We need that first. Right now we have d sigma d omega. We need d sigma d theta though. Then we're going to find sigma, which is the total cross-section, and we're going to use that to find the probability density function, because you need to normalize by sigma. So in order to find d sigma d theta, you just look at these equations. Well, sigma is the integral over all d sigma. You can express that like this in terms of the differential scattering cross-section. And here I write solid angle in terms of sine theta d theta d phi, which is by definition the solid angle. And you're integrating over the entire sphere, so 0 to 2 pi and phi, 0 to pi and theta. And then I just rearrange these slightly. So I have 0 to pi of this term in brackets times d theta. There's no phi dependence in this integral, so it's just 2 pi times this. And I have 0 to pi of something d theta, and that's equal to sigma. So by definition, this bracketed term has to be d sigma d theta, because if I integrate d sigma d theta over all theta, I get sigma. So I identify this as d sigma d theta. So d sigma d theta is 2 pi d sigma d omega sine theta. And I know what d sigma d omega is. It's given up here. So I just multiply this by 2 pi sine theta, essentially. So let's start getting into this in SymPy. So first I define theta and alpha, which of course are going to be the important variables for this video. And I always do this at the beginning, but I have these variables and I can do stuff with them. I can square theta, for example. I can take simp.sine of theta. So these are little variables that we have that we can build expressions out of. So first I define ds do, d sigma d omega, as this big complicated expression here. I'm basically just copying what they have, the expression I have. So I can take the first few lines here. Here I'm defining ds do, and I'm just basically copying this expression here, right? D sigma d omega. And I can look at this, and it basically just rewrites that in a SymPy sort of form. And ds dt is 2 pi times this times sine theta. So 2 pi times ds do, which is this expression here, times sine theta. And so I set that equal, I simplify it, and I can look at ds dt, and I get this expression here. So d sigma d theta is given by this. So now I have that expression. Now I want to compute the full cross-section sigma, which will be useful later on. And so I need to compute 0 to pi of d sigma d theta. D theta. Theta is the polar angle that goes from 0 to pi, of course. And it's tough. Good luck doing that without computer algebra. But so what I do is I take my ds dt expression, which is essentially what I have right up here. I use simp.integrate this expression. Theta goes from 0 to pi. And integrating this expression with theta is really a pain to do by hand. And in fact, I can't think of an obvious way to do it. But it turns out that it actually does have an analytical solution. This is the beautiful thing about the Klein-Nishima equation. There is an analytical solution. So I integrate it, and it turns out I have to simplify it twice. If I don't simplify it, it looks nasty. So if I just do this, and it takes a little while to run, right? It's a complicated integral. I get this sort of nasty looking expression. If I simplify it once, by the way, this is handy for SymPy to be used to. Sometimes you have to call simplify twice because it doesn't do the job entirely the first time. So I kind of had to play around with this. If I call it only once, I get this weird log thing here, but I don't know why it's not bringing this down and using the log rule. But if I simplify it again, it actually will do that. And it will have it in sort of its neatest form. And that allows me to get the total cross-section sigma like this. Remember that alpha is the incoming kinetic energy of the photon divided by the rest mass of the electron. So our cross-section, the full cross-section, is sort of interesting. So now we want to find the probability density function. And I sort of slightly talked about this before, but I want to really make this important point. So now I want to make this extremely important point. So if the incoming flux of particles is uniform, what does that mean? Well, in the diagram above, it means that they're all sort of coming in randomly, like this, all over the place. If it's uniform, then the probability of scattering at a certain angle theta, which is equal to the probability density function times d theta, right? Probability is infinitesimal because I'm dealing with continuous functions here, is proportional to d sigma d theta d theta. So this tells you how much sigma there is per angle theta d theta. So it says that the probability of sort of scattering in this ring here is proportional to d sigma. So if this corresponds to a smaller d sigma, if this black area is really small, then we're going to have less particles scattering through here. But if this black area is larger for this, and we have a uniform sort of distribution of particles, as this gets larger, if this particular ring corresponds to a larger area, then I'm going to have more particles scattering through here. So that's essentially what that equation tells you. So the probability density function of scattering at an angle theta, or scattering in that ring on the diagram, is just equal to some constant times d sigma d theta. And if I integrate this over all theta, I should get a value of 1 by definition of a probability density function. So from 0 to pi, because theta is polar angle. And that basically tells me that C is equal to 1 over sigma, right? 1 is equal to blah, blah, blah. Integrate this all. This is just the cross section. So my probability density function is 1 over sigma d theta. And of course, if I integrate this from 0 to pi, I get sigma over sigma, 0. So my probability density function, the most important thing to take out of this is it's proportional to d sigma d theta. The more d sigma I have per d theta, right? Particular theta, if that corresponds to a larger d sigma at the beginning, as seen in this diagram here, and this is a uniform flux of particles, then of course at that particular angle theta, we're more likely to get scattering there, because this is a larger area and the incoming flux of particles is uniform. So now that we have this expression here, it's pretty easy to find. So I have my sigma from part B, and I just say it's equal to ds dt, which I solved above, divided by s, right? And so if I just look at this on its own, I get this expression here, but I want to do a little bit of simplifying. So I call a simplify here, and I get this expression. It's a big, long expression. So you can see why doing this by hand would be kind of a pain. Computer algebra is really simple. So that's f of theta. That's the probability of scattering at a particular theta. So like I said, a particular theta corresponds to this entire band here. But suppose I want the probability of scattering at this particular black little box here. Well, that is given by g of theta and phi. It's 1 over sigma d omega here. And so that's a particular solid angle. That gives me the probability of scattering at a particular solid angle. So here I use ds do, which is what I have from the Klein-Nishima equation. And I can get a different PDF in terms of omega. And there's a fundamental difference between these two things here. And I have a good sort of thought experiment to think about this, right? This black box corresponds to d sigma d omega, but the whole band corresponds to d sigma d theta. Now, so here's a good thought experiment to think about this. Suppose someone picks you up and they place you randomly somewhere on the surface of the Earth, right? And so this is sort of like the Earth, this sphere that I have here. And I might ask the question, are you more likely to be closer to the poles or closer to the equator if you're randomly dropped on Earth? And you might think, well, oh, I'm equally likely to be everywhere, so equally likely to be the poles or the equator. Well, you can think of these black boxes as being like equal probability density function. And there might only be one black box at the pole, right? But like, you know, maybe 50 of them around the equator representing the solid angle. So you're much less likely to be around the equator than you are around you're much less likely to be around the pole than you are around the equator, right? So even though in your case, d sigma d omega is constant around the sphere, d sigma d theta, you're much more likely to be closer to the equator. And that's sort of what's happening here with f of theta and g of theta phi, right? This says as a function of theta, how likely are you to be somewhere compared to the pole to the equator? And g of theta phi says how likely are you to be at a particular solid angle, so like a particular almost like little box somewhere on the planet. Because if you're equally likely to be everywhere on the planet, then you're more likely to be closer to the equators than the poles. It's a very weird sort of thing to think about, but that's the difference between these expressions. So this is theta, this is like the band, and g of theta is like, the g of theta phi is like the little black box here. And so I can solve for g of theta phi here as well. I think I already did this, and I get this expression here. So I have two different expressions. And let's actually plot these two and see what they look like. So I'm going to get my PDF for theta and my PDF for omega, and I have underscore f to represent that they're a numerical function in Python. In order to do this, I call sim.lambda phi. I take my expression PDF theta, which is a symbolic expression up here. So it's symbolic, it's not numerical. And this converts it to a function. And the input arguments are theta and alpha. Theta and alpha. Alpha is the incoming energy of the photon divided by the rest mass of the electron. I'm going to continue to repeat that because I know you're going to forget if I don't continue to say that. So it gives my arguments and then my function. So I have my functions here. And I can give them arbitrary arguments because they're, you know, numerical functions. So I can give theta is equal to np.pi over 2, and alpha is equal to 2, for example. And it will return a particular value. So that's my probability density function. So let's do a plot for alpha equals 2. So I'm going to plot theta from 0 to pi. Those are the angles that it can take. And I'm just going to plug in PDF theta f, which is my function here, and alpha is equal to 2. So theta and omega. And let's actually see what the plot looks like. So here's f of theta. That's the probability of sort of scattering, or it's the probability density of scattering at the angle theta, and g of theta phi. And by looking at these plots, these are polar plots, which means that the radius, right? So I have my angle theta versus r. The radius at a certain angle is proportional to the probability density. So for f of theta, I have very small probability of scattering at 0 degrees. And that's exactly like I said. You know, the probability of scattering right here is small because there's only one box here, whereas there's lots of different boxes around this angle theta. So you're much more likely to be at, you know, a middle angle theta than you are sort of near the end. But g of theta phi says if you consider all the boxes sort of separately, you're still more likely to be in the box that's at the pole than you are near the equator. And that's something, you know, if this was the Earth and you were randomly being dropped down, this would be a circle because you'd be equally likely to be anywhere. And then this might look sort of like this. Anyways, so you're more likely to be at the box at 0 degrees, g of theta phi, if you're considering all those different solid angles. But for theta, you're more likely to be sort of scattering here. And I can change alpha. I can say, well, what happens if alpha equals 10? This means that the incoming photon has more energy. Well, then it sort of starts to stretch towards 0 degrees here. And if I make alpha smaller, like 0.1, then it sort of goes like this. So you're not, the photon doesn't go forward, the photon sort of backscatters more as it's at smaller energies, right? And that's what you can sort of see. So now let's make an animation. I'm going to change alpha continuously, and we're going to see how this sort of blob here and this blob here change. So I have theta from 0 to pi. Those are the possible polar angles it can take. I'm looking at alphas for a range. So it's 10 to the, and I'm going from -3, so 10 to the -3 to 10 to the 4. This sort of gives like a logarithmic scale here of alphas. Remember, alpha is the ratio of the energy of the incoming photon to the rest mass of the electron. So 10 to the -3 means that the incoming photon is 1/1000th the energy of the rest mass of the electron, versus 10 to the 4 means it's 10,000 times more energetic than the rest mass of the electron. So we're looking at a lot of different alphas here. And I get my PDF. I just basically do this for theta, which is this array here, and then all the different values of alpha that I have. So I get a bunch of different PDFs, one for each value of alpha. I can use that to make an animation, which is what I do here. So for the frame I just take the ith PDF, which is what I've obtained here. And at the top, I plot the value of alpha that it's equal to. So alpha is I. Okay, so the animation is finished, and you can see for small alpha, you have more probability of scattering over here. As alpha increases, the probability of theta, it gets closer and closer to 0 degrees, meaning that photon just whizzes right through the electron. It doesn't scatter, it doesn't change direction. And that sort of makes sense. If you have a heavy truck colliding with a light car, right? The truck is not going to change direction as it, you know, smashes through the car. So the more energetic photon smashing into the electron doesn't change the photon's direction as much. So more energy in the incoming photon means it scatters more often at less of an angle. So now let's look at something interesting. Let's get the probability density function, right? We have the probability density function of the angle, but let's see what the probability density function of the outgoing photon energy is and the outgoing electron energy is. So in a Compton interaction, how is the energy shared after the collision? That's a very interesting question. Does the electron take more of the energy, or does the photon take more of the energy after the collision? So we can do this with the information that we have given the angle probability density function. So the outgoing photon energy in Condensed Scattering, this is a basic second year, sort of first year physics formula. E prime, the outgoing energy of the photon after the collision, is equal to the initial energy, 1 plus alpha. Alpha is E over mc squared. Initial energy of photon divided by rest mass of the electron. 1 minus cos theta, where theta is the scattering angle. And I know the distribution of theta, so I should know the distribution of E prime. So I want to get my probability density function, which I'll call f of E prime. Same thing with the outgoing electron energy. I know that T is E minus E prime, incoming photon energy minus outgoing photon energy. That's just energy conservation. And it's equal to this. This is just some simple algebra to get this expression. And I want f of t, which is this probability density function. These are basic Compton scattering formulas. And like I said, remember alpha is equal to incoming energy of photon divided by the rest mass of the electron. So I can essentially express the PDF of E prime, right, the probability density function, as 1 over sigma d sigma dE prime. I don't know what this is yet, right, but this is sort of what I want to find. But I know this is equal to 1 over sigma d theta, and then chain rule, d theta dE prime, right? I'm just saying d sigma d theta dE prime, and then I write this as inverse, so dE prime d theta inverse. So if I have all these variables, right, I know what E prime is in terms of theta, I know what d sigma d theta is, I know what sigma is, so I should be able to find f of E prime. So here I define E prime, alpha, t, and theta again. And I'm going to get an expression for E prime in terms of other variables. So E prime is equal to E over 1 plus alpha minus 1 minus cos theta. So I have this expression for E prime, and I also have E prime itself. You might be wondering why I'm doing this. Well, I know what all this is in terms of theta, but I want to know what it's equal to in terms of E prime. So I want to know what theta as a function of E prime is. Because then if I get all this in terms of theta, I can substitute in theta, which is a function of E prime to some extent, right? I can just invert this formula to get f as a function of E prime. And you'll see that in a sec. But basically what I do is to get theta as a function of E prime, I set E prime minus E prime expression, right? Which is essentially E prime minus the thing that E prime is equal to 0. And then it'll solve for theta in terms of all these variables, right? If I want to solve for theta in terms of E prime, it's the same thing as setting this whole thing equal to 0 and solving for theta. So that's what I do. I set E prime minus E prime. E prime minus the expression of E prime. I solve it with respect to theta. And there's two solutions. They're just sort of off put by different angles. You'll see what I mean. There's sort of 1 plus 2 pi and this. They're basically equivalent, so I just take the first one. And I get theta as a function of E prime. So this is that theta is equal to minus E plus E prime alpha plus E prime over E prime alpha. So that's theta as a function of E prime. And then my PDF E prime, which is what I have here, I just substitute all these expressions. So I say 1 over sigma times d sigma d theta divided by the derivative of E prime with respect to theta, right? So I divide by dE prime d theta. And you'll see it's exactly like I said. I plugged all these things in, and I get an expression here. But the problem is this is in terms of theta, but not in terms of E prime like I want it to be. But I know what theta is in terms of E prime, so I can substitute this, which is equal to theta, for every one of these thetas in this expression here. And you can see again why this would be a huge pain to do by hand. So for each of these thetas, I plug this in. That's really simple to do in SymPy. I just say my new expression is equal to the old expression where I substitute theta. So every time I get a theta, I put in theta expression, which is this expression here. And then I simplify it. And I can run the cell and I get this. So now I have my PDF as a function of E prime. It's a very complicated looking expression, and again, a real pain to get by hand. And we know that this should be normalized to 1. Like writing it like this, f of E prime should automatically integrate to equal 1. And we can check that. So examining the expression of E prime, I'm just going to integrate from theta equals 0 to theta equals pi. So that corresponds to at theta equals 0, E prime is equal to E. So that's my first bound of my integral is E prime equals E. And at theta equals pi, E prime is equal to E over 1 plus 2 alpha. Just looking at this expression here. So I need to integrate from this expression here. E prime goes from E to E over 1 plus 2 alpha. This is what this is. Integrating in SymPy, my expression, the variable is E prime. So this whole expression, I'm taking E prime goes from E to E over 1 plus 2 alpha. Again, real pain to do by hand, but very easy to do in Simplify. I can run this cell. It takes a little bit because it's not an easy thing to integrate even for SymPy. And you'll see that indeed I get a value of 1. So it is indeed normalized, and I have my PDF. So basically everything for the kinetic energy is very similar to everything above. It's just like another example of this. So my probability is a function of t, which is the kinetic energy of the electron after the collision, is 1 over sigma dt. I do the same thing as I did with E prime above. And this is basically just rehashing all the code except with t. So I write down my t expression. Then I solve for theta. I solve for theta as a function of t, but the same way I did everything above. I get my PDF, and then I substitute in what theta is in terms of t, and I get my PDF of t. You can see that I get the following expression here. And again, this is very complicated, right? This is the probability density function in terms of t. So let's also check that it's normalized. So examining this expression, when theta equals 0, t equals 0. When theta equals pi, t is equal to 2e times alpha over 1 plus 2 alpha. So I integrate this expression, which is this whole thing here. T goes from 0, the first bound, to 2e alpha over 1 plus 2 alpha, the second bound here. And again, check that it's normalized. Spoiler alert, it is normalized. And the value is equal to 1. So I want to make a cool animation. Like we have our PDFs, let's actually plot some stuff. So like before, I use Lambdify to convert my symbolic expressions for this PDF and this PDF in terms of numerical Python functions. So the arguments are e prime, e, and alpha for the e prime PDF, and t, e, and alpha for the kinetic energy of the electron PDF. So these are just functions that take in 3 variables. And let's plot a sample for alpha equals 2. So the mass of the electron is 511 kilo electron volts. So I set that equal to 0.511 mega electron volts. I'm going to set alpha as 300, meaning that the incoming photon is 300 times more energetic than the rest mass of the electron. Energy, the incoming energy is alpha times m, because by definition, E over m equals alpha. So I just use this to find E. I set my bounds for E prime and my bounds for T, right? This is the lower bound for E and the upper bound for E. Same thing for T. That's just from looking at sort of these boundary conditions here. You can't have more kinetic energy. There's a limit to the kinetic energy the electron can get, and it's equal to this. And there's a lower limit to how much energy the photon can lose as well. And then I just plot it. And so what I'm plotting here is, rather than plotting E prime and T, I'm plotting, and I'm going to, instead of m times alpha, I'm just going to divide this by E. So this is the energy of the photon after the collision divided by the initial energy times 100. So this is the percent of energy that the photon keeps. This is the percent of energy that goes to the electron on my x-axis. And here I'm plotting the PDF of both the photon energy afterwards and the kinetic energy afterwards. So my outgoing photon and electron. And you can see that I have a figure that looks like this. So here in this case, where alpha is very large, my electron gets most of the energy. So my very energetic photon smashes into the electron, and the electron absorbs most of the energy. But for smaller alpha, let's say alpha is equal to 2, it's a little more interesting, right? The electron still takes more of the energy here than the photon, but it's not taking all the energy. So the photon more often, remember this is probability, the photon more often will lose this energy, and the electron will be getting more energy. But it's still possible, of course, that the electron takes very little energy, and same thing with the photon. It's a probabilistic theorem. If alpha is very small, then you get something interesting. You get that the photon basically keeps all of its energy, and the electron keeps all of its energy as well. And when the energy of the photon is small, it basically will scatter right off the electron, and the electron absorbs nothing. It's like throwing a bouncy ball at the floor, right? The ball absorbs all of its energy. It's like elastic scattering, and the floor doesn't really gain much of the energy at all. So that's sort of what's happening here. So I want to create an animation where this plot sort of goes as a function of alpha, and you'll see as alpha gets bigger or smaller, how these two curves change. So like before, I create a bunch of different alphas. From this, I get a bunch of different arrays for my E primes, the outgoing electron energy, the T's for the kinetic energy of the electron, and my PDFs as well. So I'm basically just using list comprehension to get a bunch of different arrays, each for a different value of alpha, as opposed to one value of alpha. And then I can index these arrays to plot. So my frame number I is going to be, proportional to, or it's going to be used to index one of these arrays. So this is like a list of NumPy arrays. And so I take my alpha value, my E prime, which is my array of E primes, and my T, which is an array of kinetic energies. And I do the same thing as above. So E is equal to m times alpha. And I plot the proportion of energy going to the outgoing photon and the proportion of energy going to the electron. Remember, it's probabilistic. And then I can run the cell and we'll create an animation. So here I have my animation. You can see that as the photon energy becomes higher and higher, the outgoing photon has less and less energy, and as the photon energy gets higher and higher and smashes into the electron, the energy of the electron, it takes most of the energy from that collision. So like I said, analogous with a bouncy ball, you'd see a similar plot like this. As you drop a bouncy ball, think of the rest mass of the Earth as being really heavy, and the kinetic energy of the dropping ball is really small. And then when it's small, the ball takes all of its energy. So that's like the photon, right? As the energy of the photon is small, it absorbs all its energy, and you get sort of an elastic collision. And as the energy becomes more and more, it's actually the thing that the ball collides with that takes all its energy. So the electron gets all the energy. Anyways, I hope you enjoyed this video. If you did, please be sure to like and subscribe. You made it all the way through. That's very impressive. You're one of maybe 5 or 10% of people that watch my videos. Be sure to join the Discord server as well. We have almost 1,000 people there now, and it's a really good community for asking questions about basically anything math or physics related. There's a lot of people helping people with questions they have about random problems. Anyways, I'll see you next time.